now it's Professor Dr. Isabelle I.Ripp-Baudot. As I said, she is a research in the IPHC of CNRS. She's the group leader of Belle II experiment here in Strasbourg, and she's part of the QMat direction of QMat. She will talk a little bit about the search of new physics in the Belle II experiment. So please, Kema, welcome.
Thank you. Thanks. So first, I would like to thank the organizers and in part Denis and Manuel for giving me this opportunity to present my research field. It's always my huge pleasure to share my passion about particle physics. And so today, for the second part of this QMat Cafe, I propose to explain how particle physicists look for what we call new physics, and how we do that in the Belle II experiment in particular. So I will focus on one particular measurement, which is called RD star. Up to go to the next. Yeah. So before speaking of new physics, I must first introduce the standard model of particle physics. So our goal in particle physics is to write the Lagrangian. And I like very much the Lagrangian, so I can't refrain speaking of it. The Lagrangian of the most fundamental constituents and their interactions. So most fundamental means currently known as such, since this concept evolves with experimental precision and thus with time. So as of today, the size of the smallest pieces of matter known to us and called particles for us is about 10 to the minus 18 meters, corresponding to energies of the GeV to the TeV scale. So such space and energy scales are described by special relativity and quantum mechanics. And thus, particles are mathematically described by a renormalizable quantum field theory called the standard model. So there is also a standard model in cosmology, but for me, the standard model is the standard model of particle physics. So evolution in space and time of all fundamental constituents are derived from the Lagrangian written here. It includes the quantum fields describing all fundamental particles, the bosonic fields for the interactions, the fermionic ones for the matter, and the scalar one for the Higgs field, with interactions implying at least 3 fields, 3 or 4, so interactions between different particles, and propagation, it's where only 2 fields are together. So, and the space-time covariant derivative here contains, on the one hand, the kinematic term of the Lagrangian, you know, it's T minus U, but on the other hand also, and it's very important, a term describing the interaction. So this Lagrangian is very simple to write, as you can see here. It fits it fits in one line, and you can easily display it on mugs and T-shirts that you can buy at CERN. But you can also look very smart in math and develop all the implicit summations I didn't spoke about on the previous slide that were hidden. And you can write several pages of this Lagrangian like that. So to constrain the structure of this Lagrangian and thus what transitions are allowed or not between particles, the key word is symmetry of nature. We like big words. So I guess you well know how conservation of a quantity in a transition between initial and final state is associated to an invariance of a physics law, so the Noether theorem, or a symmetry. Here I remind about energy, momentum, and spin conservation. I will not take time on that. But those are associated to continuous transformation in the well-known 4D space-time. However, in a quantum field theory, we must also consider a bit more complex transformations, less intuitive, that can be discrete and lead to various conservations like the baryonic B number or the leptonic number, parity, etc. Here I must stress that though these symmetries were considered to be strictly observed during several decades, some of them are now reconsidered in the quest for beyond standard model physics. Another class of symmetries are the gauge symmetries, which are the central pillar of our Lagrangian. There are global gauge symmetries, leading, for instance, to the conservation of the electric charge, but there are also local gauge symmetries. Very basically, you don't want your quantum field to depend on an arbitrary phase. So these local gauge symmetries lead, it's really like magic, they lead to the existence of the fundamental interactions. You don't introduce them by hand in the Lagrangian, but you ask for some symmetries and they appear, as I said, more or less like magic. So our standard model is commonly summarized by this picture showing all matter particles here, and the gauge bosons mediating interaction in orange, and also the scalar Higgs boson. So the Higgs does not appear due to a gauge symmetry. So it's not a fifth interaction, that's how we say it. But it is put by hand, ad hoc, in the Lagrangian, because the usual Lagrangian mass term is forbidden by a given symmetry, which is the electroweak symmetry. Maybe you may also notice that gravity is not included in this picture. You have a strong interaction, electromagnetic interaction, and weak interaction, but no gravity. So this does not upset us. It's indeed not yet included in the standard model. It does not upset us because at this particle scale, gravity intensity is totally negligible with respect to the intensities of the other interactions. But we know that this will not be the case anymore at ultra high energy. So actually this picture looks simple, but there are many, many symmetries and many information hidden behind this sketch. So with this slide explaining the evolution of our universe, I want to make you aware of the link between cosmology and particle physics, since what we nowadays think to be the most fundamental pieces of matter are the physics objects populating the very early universe aged of, let's say, 10 to the minus 10 seconds. But you can understand here that what we thought to be the most fundamental pieces of matter evolved with time. One day we thought it was atom. It was atom. So now we describe objects here. So then with expansions of the universe and decreasing particle densities, the interaction probability between these particles is decreasing also. And fundamental constituents tend to cluster together into more composite objects like hadrons and later nucleons and nuclei and atoms. After several millions of years, gravity will take over the three of our fundamental interactions and large-scale structure will be formed, and we enter the field of the previous talk. So the status of the standard model of particle physics is particularly impressive as far as its precision and predictive power are concerned. Many predicted particles like Z and W bosons, the top quark, the Higgs boson have been predicted and indeed observed later. And this plot here on the right illustrates the excellent agreement between predicted values in the framework of the standard model and their measurements. So these bars here represent what is called the pool, This means the predicted value minus its measured value divided by the uncertainty. So if predictions are accurate, all these bars should be distributed Gaussianly around 0, as it is indeed the case here. Maybe one word on the fact that we speak of standard model rather than standard theory. That's what I forgot to mention here. So this is because, as I understand it, as expected from a theory, it is based here on very fundamental concepts, so like symmetries mainly. So, but then we add by hand many other ingredients, like there are 3 families of fermions and not 1, 2, or 4, with which theoretical ground is not understood. It's not explained by the standard model. We put it by hand. So now, though this great success, we, at least in particle physics, we used to say that this theory is most precisely tested. There are actually many phenomena that we are not able to explain in the standard model, though they are undoubtedly observed, like the absence of antimatter in the universe and the existence of the dark energy. And measurements show that what we managed to explain by physics laws, so the physics we are all studying, consists only of 5% of the universe component. So besides that, there are also questions we would like to answer. If we are not satisfied by an explanation like the anthropic principle, these questions are, for instance, why 3 families of fermions I just mentioned, or also where the 3 parameters of the standard model come from, not speaking of the values of fundamental constants, and so on. So the conclusion is that the standard model is a theory valid only at a given scale, and a new theory is needed at higher energies to describe the content of a younger universe. So this new theory can be an extension of the standard model with more global or additional symmetries showing up, or it can replace totally the standard model. And to understand that, it's the same when you must extend classical mechanics to special relativity when speeds become too high. And you must, so this is an extension of classical mechanics, let's say, and you must replace classical mechanics by quantum physics when dimensions are too small. So one particular intriguing puzzle I illustrate here is where the symmetries observed between leptons and quarks, both are fermions, come from. So you have 3 families of quarks, 3 families of fermions. Because of some symmetries, we build a doublet of in 3 families. And you see some symmetries if you they look very similar at first view, with flavor transitions between lepton flavors and quark flavors. But when close up, we see huge inexplicable differences. And that's one question we are working on in my experiment. So in the end, there is no doubt that we must go beyond the standard model. And we call grandiosely this the quest for new physics. The question is, of course, how to go beyond the standard model. So on the theoretical point of view, either you describe explicitly each new field in the Lagrangian, as we just saw it for the standard model, but this needs that you know the new physics, or you can use an effective theory that does not need to know a priori these fields under the assumption that the current experimental sensitivity, our current experimental sensitivity, is below the scale of this new physics. This is the same procedure as the description of the beta decay, you well know, I guess, without knowing about the W boson and the quark content of the nucleon. Sorry. the Fermi constant is actually a quadratic function of the weak coupling constant divided by the scale of the new physics here. And it's the same in the effective Lagrangian for new physics. So since we have not seen yet effects of this physics beyond the standard model in our measurements, either the coupling constant here of the new physics coupling to known standard model particles is very small, or the scale where the new physics shows up is very high, or unfortunately both. And in this case, there is no much hope to find anything in the coming years, at least. So that was for the theory, but now what about the experimental search for new physics? For that, let me present my experiment called Belle II. We say that it searches for new physics at the intensity frontier, and I will explain what it means. So there are actually two ways to search for new physics in particle physics. One is very basic, I would say. It consists in trying to produce physically new unknown particles on their mass shell. If we believe that new physics has not been discovered yet because it shows up at a very high energy only, that is not yet accessible, this approach needs a very high energy. So this is what it is pursued at the LHC collider located at CERN that delivers proton-proton collisions at the highest energy ever produced in a particle collider. So the second approach, illustrated by the second blue and red plot here, is consists in comparing very precise measurements to very precise predictions that need to know which intermediate particles must be taken into account in the theoretical prediction to do the calculation. So any discrepancy between the prediction and the measurement would be due to forgotten unknown particle contributions in these intermediate loops. So this method requires utmost precision. That means experimentally the smallest possible statistics and the smallest possible systematics uncertainties. In other words, huge, respectively, huge number of collisions and very clean collisions. And this is what Belle II is about. So this indirect approach, search for new physics, is potentially sensitive to much higher scales of the new physics than the direct search. It's illustrated on that plot, but it's a bit long maybe to explain. You have the coupling constant I spoke about in the previous slide, and here the mass scale lambda of the new physics. But maybe I can say that indirect searches are like looking for a tunnel effect that is due to quantum mechanics seen at a classical scale. So the Belle II experiment consists of the Belle II detector. That is a typical huge cylindric detector I didn't put on that slide, made of many pixelated layers of different materials like silicon, instrumented lead, liquid argon, etc. And located at the collision point of the SuperKEKB electron-positron collider, which is a circular collider, like the CERN in Geneva, but this one is smaller and located in Japan. So I just spoke of how to achieve utmost precision thanks to very intense beams to have lots of statistics. And in Belle II, this is made possible by a recent breakthrough in accelerator physics with a new collision scheme of nano-sized beams in transverse direction. And we call that pencil beams because they are very flat. We can compare their transverse dimension of these beams, which is 50 nanometers, to the LHC beam dimensions, which are of the order of a few micrometers. So with this collision scheme, SuperKEKB, the accelerator, will be the most luminous collider ever operated in the world. And therefore, the Belle II experiment, which will register collisions delivered by SuperKEKB, is said to be at the intensity frontier, while we speak of the energy frontier for LHC. So we expect to overpass the current collider luminosity world record by a factor of 40 in the coming years. You can see here that this is on the y-axis what we call the luminosity, let's say the intensity, and here the collision energy, and LHC is at the highest possible energy ever, and SuperKEKB is at the highest luminosity ever. And all those colliders here are now stopped. Maybe still, wait, one slide. So such very large scale experiments I didn't speak of the dimension, for instance, of the detector, which is something like 8 meters long and it's cylindric, so 8 meters for the diameter. So such very large scale experiments cannot be performed in your lab on a tabletop experiment, of course, and need the collaboration and the financial support of many institutes in a very international context. And in the Belle II experiment, we have more than 100 labs working together from almost 30 countries. And the participation to such an experiment is decided at the highest level. And I'm always proud to show here the picture of the, and this is me, of the official ceremony of the French flag rising in Belle II in Japan, organized by the French ambassador in Japan. So we cannot decide by our own to join such an experiment. So I don't know if I stop here to discuss what was shown up to here, or if I go on. Because on the next slide, I will focus on one particular measurement for which Belle II is a unique place for an indirect search for new physics.
So if there is any questions at this point, you feel free to do it by YouTube or here in the chat. In the meantime, I have just a couple of questions. When you mentioned that you compare very precise measurements with very precise simulations, that does mean that you consider more than one loop calculations?
More than one group? So
loop?
Loop, yes. So it's not simulations, it's really quantum calculations. It's precise. The only thing on the precision indeed is that, so the standard model is, you can make, how do we say that? Limited development. There is another word. Yeah, sorry, in English.
Restrained.
Taylor expansion, I think.
Maybe I'm looking for another word. Sorry. But I can show you. I don't know if you have ever seen Feynman diagrams. So you see here, each time you have a gauge boson coupling to a fermion, you have the constant coupling constant of this interaction. And the module of this coupling constant is smaller than 1. So that's why you can do a series as a function of power of this gauge coupling constant.
Okay.
For each loop, you have twice, for instance, sorry. Here you have, forget about that. Here you have twice the coupling constant. So it's squared and to the 4th. So for each loop, you will have less and less corrections to add to your calculation. Because for instance, this process, let's imagine here, an electron and a positron are colliding. They give, let's say, a photon, well-known things. giving electron-positron in the final state here. Forget about red and blue and new physics. So this is the first order of the calculation. So I can say to a theorist, give me the rate of this process. And if he takes into account only that in his calculation or her calculation, the precision will be limited. So for me, I don't care about series of the gauge coupling constant because I do a measurement, I have the whole nature in it. But the theorist has to take into account this, and then the photon radiates or creates an electron-positron pair that can be reabsorbed, and you have all momenta possible, and you have infinite numbers of loops that can be emitted like that. It's more or less the thing that the vacuum is not empty. Mm-hmm. And he has to, or she has to take into account all this in the calculation. So you decide the precision with the numbers of loops you take into account. Okay. So the idea is to match the theoretical prediction precision to the experimental one, and they have to fit. And if there is a discrepancy, then it's interpreted as either an error. Of course, we first try to check that nobody did any mistake, or there are unknown particles who participated we are not aware of, and it's a new physics contribution, quantum manifestation of new physics. I don't know if it's clear.
Yes, yes, it is. Thank you. Just a tiny more question. It's the Belle detector. It's similar to Atlas and CMS.
Yes,
I mean,
yes. So if you have you been to CERN or not?
Not in the detector. Sorry.
Yeah, because it was running. So yes, the only thing is that Belle II is very small with respect to Atlas and also to CMS. I think CMS is maybe 25 meters long. I don't remember now. And okay. Belle II is less than 10. So it's, let's say 1/3, something like that.
Okay, good. Thank you.
But the principle is the same.
So I don't see any questions here. I don't know if in YouTube, Denise, there is any questions?
Nope,
at the moment?
nothing from YouTube. I asked and nobody answered. So
okay. So
I go on. Yes. So yeah. I propose here to present you one particular very hot result currently, which is extensively discussed since a few years in our international conference in the field. It concerns fundamental symmetry called Lepton universality. So this is that in the standard model, the coupling of gauge bosons. So I could have put gamma, but I put a Z, I don't know why, to leptons is described as being flavor blind. If you calculate this transition, you will get the same number more or less if you put E plus E minus in the final set, or mu plus mu minus, which is heavier electrons, or tau plus tau minus, which is the third family, so even more massive lepton of the same kind of as the electron. So you have just small corrections to take into account due to the lepton masses. So this is called the lepton universality. So though this symmetry has no fundamental ground, it is formally expressed like that in the standard model, in the theory, according to what has been always observed experimentally. So you can see here, these are measurements. You can find them in what we call, it's our Bible, it's the particle data group booklet. You see very a precise measurement of rates of Z going to mu mu with respect to Z going to EE and so on. And you see that it's totally compatible with 1. So that's why we put by hand this symmetry in the standard model. So these observations of lepton universality stand for many decades. And it is only very recently that some puzzling measurements were published questioning this lepton universality. So 3 different experiments operating at 3 different colliders, E plus E minus or proton, reported discrepancies between the measured value and its theoretical prediction of a quantity that is called RD star, or sometimes also RD. So this quantity is a ratio of transition rates. Sorry, it's a branching ratio here, that it's like transition rates of B mesons decaying to a D meson, a tau lepton, and a neutrino, or a mu lepton and a neutrino. So this ratio can be very precisely calculated in the framework of the standard model. So here I hope you're not too much lost by the zoology of particles like B and D mesons, but you don't need actually to know much about it. Nevertheless, I say a few words. The B meson contains a quark called bottom and another quark, and the D meson contains a charm quark and another quark. And this transition from B to D, or from B quark to C quark, is made through a W boson, as it is illustrated on this Feynman diagram. So the only point is that this ratio measurement can be performed with a D meson or a D star meson, which is just an excited D meson. We don't mind. So here you can see a display of the many measurements performed by the 3 experiments I spoke of, with their uncertainties depicted by the ellipses here. So you have, for instance, one experiment in the US called Babar that measured RD somewhere here in the middle of the black ellipse, and also RD star like that. And you have an uncertainty on RD star and an uncertainty here on RD, and the one standard deviation around their measured quantity is an ellipse in 2D. And you have also the 3rd experiment is at the LHC, and they can only measure RD star, not RD. So they made these 4 measurements, and their uncertainties are depicted by the error bars here. So the very precise theoretical prediction is represented here by this gray ellipse. And you can notice that it's very precise with their precision level is much better than the experimental level currently. And you can also see that there is a discrepancy, let's say, 4 sigma disagreement, 4 standard deviation disagreement between prediction and observation. So I guess you know Gaussians and have some basics in probabilities and statistics. And you may know that with 3 standard deviations, you are expected to include a real value with a confidence level of 99.9, I think, %. And hence this result is significant. The discrepancy is significant. However, because estimating an uncertainty is a very tough task in physics, and maybe in particular in particle physics, we used to ask for 5 standard deviations to claim any discovery. So the current situation is this one. We cannot claim for a discovery yet, but maybe it is. We cannot conclude if what is observed, let's say, is a rabbit. I mean standard physics with a W-mediated transition here, or a duck. In other words, new physics with, for instance, a supersymmetric additional Higgs being responsible for these transitions, and for the measured anomalies we just saw with respect to the theoretical predictions. So as I said, we are not yet at the stage of being able to firmly announce a discovery, and that's why Belle II results are eagerly awaited by the community. So now how to progress on this half discovery. If we look at the current measurements, so the ones I just showed you, I picked up here two as illustrations. First, the ones performed at LHC, so those were the only bars because the only measurement of RD star. So it's done with hadronic collision. It's a proton-proton, where they were all systematically limited. So if I give the detail of their measurement, so I took one from the plot I showed in the previous slide. There is an uncertainty due to the limited numbers of collision they study, and something which is due to systematics uncertainties. And you see that because then to have the global uncertainty, you have to do the quadratic sum and take the square root. You see that it's definitively systematically limited. So LHC is currently in shutdown and will resume operation next year or early 2022, I don't know yet, to accumulate more data, but even with more statistics, this will not help improving this result. So while measurements at E plus E minus collider, so electron-positron, were definitively statistically limited in the plot showed previously. So I give one example of one measurement here, one ellipse. And for these measurements, all E plus E minus data in the world were used. So no improvement can be expected either. That's why we need a new experiment, which is Belle II, who is now the only E plus E minus experiment in the world for this physics, and it is expected to register 40 times more data than currently available. I spoke of that when I presented SuperKEKB, and I spoke of intensity frontier. So here I would like to just add one word about the fact that in the past, let's say 20 years ago, many colliders existed in the world. If you remember, I showed this plot and I said all these colliders are now stopped. So really many in different international or national laboratories like Fermilab, SLAC, DAISY in Hamburg, everywhere in the world. But nowadays, only 2 particle colliders exist to search for new physics beyond the standard model, which are the LHC at CERN in Europe and SuperKEKB in Japan. So this slide is to understand why we need not only the LHC, but also E plus E minus collisions to progress in the quest for new physics, and in particular on the measurements, the kind of measurements I show here, precision measurements. When you do a collision between protons with very high energy, the proton is a composite particle. It's not a point-like particle. And the collision actually occurs not between protons, but between its constituents, either quarks or gluons. If you are at very, very high energies, like at the LHC, even those 3 valence quarks are mixed with what we call the C quarks and gluons. We speak of partons. While we know the energy of the proton beam at the LHC, so you have here a collision with this illustrating the momentum of the beam, we know it, but we don't know what is the energy of the one particular fragment or parton that makes a considered collision, gluon or quark inside the proton. It carries an unknown fraction of the proton energy. So we can only describe statistically the collisions, but not individually. Moreover, the collisions create quarks or gluon in the final state or not final, but because these gluons and quarks cannot remain like that because they are colored particles. They immediately hadronize, and this process produces jets of many, many particles, leading to a very crowded final state to be detected by our detectors, as it is illustrated by this real event display of an LHC collision registered in the LHCb detector. So here it's LHCb has the particularity, it's not a cylindric detector. It's plates of instrumented of detectors put one after the other. So here you have a view shown along the beam axis. So you see that this very busy environment is not ideal to make very precise measurements, because you have to detect and precisely measure all these particles in the detector. And that's why they are systematically limited when they try to do precision measurement. So I must say that I'm very biased, because I don't know if it's Dennis or Manuel. He said that I used to work in CMS, but of course I choose to join Belle II. So I don't say here, nevertheless, that LHC is not a good collider, but its strength is elsewhere than in precise measurements, namely in the very high energy for the collisions and the very high process probabilities at these high energies. You can compare here to the event display of an E plus E minus collision registered recently by Belle II. So here this view is a transverse to the beam. The beam come from you and go into the plot. You can notice that the final state to be detected, so these tracks here detected in silicon detectors, is much cleaner because there is no hadronization. Moreover, the collision occurs between two point-like particles, an electron and a positron. Maybe they are not point-like, but we never discovered it. We are not sensitive to their compositeness at the energies we can reach. So this leads to the fact that we are well able to reconstruct the initial state and the final state for momenta. And because we know well the beam, which makes the collision, and we can reconstruct fully the final state. So in such collisions, the two beam mesons are produced in a quantum entangled way, so that we can infer a lot of information on one meson thanks to its partner. If we know information on one beam meson from quantum entanglement or EPR, let's say Einstein-Podolsky Rosen, we can have lots of information on the second beam meson. And this is very powerful for precise measurements. The drawback is that we are not able to produce such nice collisions with very high rates at the energy frontier. We cannot have at the same time highest energy and highest intensity. That's why direct searches are mainly pursued at the LHC, while indirect searches are mainly the privilege of Belle II. So I'm almost done. Before concluding, maybe I cannot refrain from saying one word about machine learning, since this is a key tool that revolutionized also our field recently. Or maybe not recently, but more and more. And the precision of our measurements is mainly made possible because of these tools. So in particular, for the RD star measurements I just spoke of, it relies on the reconstruction of the partner B, because we produce 2B in the collision. And this partner B can decay in more than 10,000 different final states. So times have changed and I am a bit old, I'm aware of that. However, at the time of my PhD thesis, I spent a significant part of my thesis to reconstruct one B decay chain. So here I speak of more than 10,000. So still nowadays, it's an impossible job to reconstruct thousands of decay chains one by one. So that's where machine learning enters the game and leads to tremendous breakthrough in efficiency and purity that translate to reconstruct let's say, the whole collision. And this translates to huge gain in effective statistics and decreases the statistical uncertainty of our measurements. So now our students, in particular Luca, who is listening to me, have become, or Luca will become, experts in machine learning, which actually has become obsolete and start to be replaced by deep learning, but this is another topic. So sorry, I was maybe a bit long, so this brings me eventually to my conclusion. I will not read it aloud because it's basically a summary of what I said. But please follow us on Twitter and Facebook and put some message. We are happy of that. Thank you.
Thank you very much, Professor Isabelle. Yeah, thank you very much. So, so clap, clap. So yes, if anyone have a question, please in the YouTube channel or here in the Zoom meeting, please feel free to raise your hand and yeah, of course. Let's to unmute. Now you have to activate your microphone.
Okay, hello.
Hello.
Thank you, Isabelle. I can't find it. I never find the hand that, I mean, it's
yeah, I didn't find it either, so sorry.
Whatever, doesn't matter. Thank you for the nice talk, and it's very interesting for me. I'm not at all in this field, so I always get little éclairage from different sides, and trying to get a global picture from that is pretty hard, but it's good fun. My specific question was, what do the training sets look like for your machine learnings in this particular case? Because you need to have a big collection of
yeah, so
data.
Yeah, so we do it mainly with simulations, of course. So we simulate large batches of the signal we are looking for instance, and all for the background, what we call the background. So all the other processes that we well know because they are standard model, we can simulate, or for part of them, sometimes we can use real data. But it's mainly based on simulation. So lots of CPU. That's why now we also switch slowly to deep learning, because the gain in CPU might help. Maybe not the gain performances, but in the end, CPU.
So in your field, you consider that the simulations are realistic enough to avoid entering biases or things like that?
Yeah, our chance is that we now pretty well know the standard model. So yes, for that, we are used to evaluate the biases due to detector effects when we detect the particles, finite resolution of our detectors, and we are used to model that. And we also are used to check for each input variable many distributions in real data and in simulation to check if we don't introduce any bias. But of course,
I had a family interruption. Sorry, that was a bit disturbing for a second.
But of course, this is the main. This translates in the end in the main systematic uncertainty.
Right. Yeah. I have other comments that are also at the margin between particle physics and astronomy. Shall I enter those now, or shall I let other people ask more questions to you?
Oh, please continue.
So first, a comment which I thought was fun while listening is that it seems that some of the motivation for your work comes from the fact that some reactions that were thought of as simple as and well understood ended up not being quite so simple as people thought, and that sort of reminded me of what Rashi is doing, which is the same. Really, these globular clusters are objects that we thought were really simple, and suddenly they turn out to not be so simple, and suddenly it opens up a whole field of new research that will probably bring lots of new answers to fundamental questions in astronomy. So you seem to have the same way of progressing, which is cool. But my question was on all these intermediate reactions that can happen in a simple collision, and that you associated with the fact that, you know, empty space is not empty. Yeah. And we very regularly hear in astronomy about dark energy, and about how the universe is expanding because of this existing dark energy, and there my knowledge is always extremely limited. And the only thing I always hear is that when you sum up all these reactions that you can have in the microscopic world in your field, the kind of energies of empty space that you get are like 10 to the 40 times higher than what we need in astronomy. Like enormous.
Yeah, it's a factor of I don't remember.
I think it's 10 to the 40.
100. Oh, yeah, okay,
or even
okay.
More, at least something really enormous. So, do you have any comments on how you see that? How is that possibly? I mean, how can people continue to work with this enormous discrepancy and not just give up on everything and just start from scratch?
No, I think we don't. I can. It's also at the margin of my knowledge when we speak of dark energy. So sorry, I cannot answer exactly this question, but at least what I can say is that now we pretty well understand. It's really a matter of effective theory. We know that the standard model is exactly true at our energies. So we are not afraid of doing something wrong. I don't know if you understand. You know that if you are in a car, the classical mechanics is a good theory. You are not afraid of.
What's the scale that matters there? Is it just the size of which you consider things? You're talking energies, but the energies should be, no, they're different, I guess.
So
no,
if I can make a comment there, I think
please.
the problem that you are suggesting to tackle, it's the problem of the merging the relativity, the cosmology with the standard model, and that's a very tough, I think, task.
Yeah, exactly. I'm aware that it's completely difficult, otherwise it would be solved.
Because you can calculate the cosmological constant in either cosmology and standard quantum mechanics, and then you will find that there is a difference of 75 order of magnitudes, and that's like what? But of course, yes. I mean, I'm not in high energy physics, but I am aware about this problem. So yes, sometimes I also question myself if doing quantum physics is still okay.
That's exactly what I said, and that's the quest for new physics. We know that I don't believe quantum physics, but that's another topic also. But let's say we know that quantum physics is correct at the scale we are doing our measurements. That's why I spoke of a tunnel effect, or what
I would like to specify is what you call scale.
Scale, the scale of energy, of the energies we are able to challenge now. So typically the TeV scale, because
But how does that relate to anything that happens in empty space today? What would be I mean, we talk about energy density, like how much energy there is per cubic centimeter or something like that.
Yeah, but
you talk about particle energies.
Yeah. These measurements of the dark energies, they come indeed not from collider physics. They come, of course, from supernovae measurements. So I don't know how to.
Maybe put it a little bit in context. The Planck scale is the limit at the moment for the high energy physics. We cannot go below the Planck scale, which is in terms of h bar. So I will say that's the the limit at the moment for the experiments.
No. So our experiment, the limit, the Planck scale is a theoretical limit. It tends to the 19 GeV. It's let's say a philosophical limit, like the smallest quantum. Or but our experiments currently, they are in the range of energies of our colliders. So the highest energy. Then we do measurements also. For instance, Ariane knows probably more than me, but in ultra high cosmic rays. Here we can reach peta electrovolts, but we don't know anything about the initial state of these cosmic rays we detect on the Earth. So it helps for maybe more astrophysics, but not for particle physics fundamental questions. So we can have
I think we still have a few things to learn.
yeah. We are not unemployed. But I hope I managed to make clear that this field is really very it's a passion.
So I have a question also. Technically, it's not mine, it's from YouTube. So it's Yen from NTU from Singapore. He's an exchange student. So we have someone from another country. Manuel asked before. He was asking the question. So he has no background in particle physics, but he was wondering what does increasing the diameter of the particle accelerator do? So I guess if you have the ring, what does it change if you increase the diameter?
So you know all in physics that you accelerate charged particles with electric F equal QE. So you will accelerate your particle with the electric field. So that's how we do in particle physics. But so you can have linear colliders. But then the problem will be that you collide the beam once at the end of the linear collider or in the middle, because you have two beams colliding in the middle of the particle collider, and then you will lose the beam. You have to produce again a new beam to collide the second time and so on. So we do also circular colliders, so that your beam can circulate, not forever because it will degrade, but during a long time, and you collide at each revolution. But when a charged particle is bent, you also well know that it will, rayonner, it will emit.
Radiate, maybe.
Yeah, radiates, yes, sorry. It will emit or radiate photons, for instance, for an electron. You have synchrotron radiation, bremsstrahlung, things like that. So you will lose energy. So this is, the more you bend your particle, the more it will radiate. So indeed, if you increase the diameter, you will manage to not lose too much energy due to radiation and increase the energy of the collision. So that's the idea of the future circular collider in project at CERN. It's a 100 kilometer for the circumference circular collider in the Pays de Gex near Geneva. But of course, you can imagine that digging a tunnel of 100 kilometers under the ground in a populated region has a cost. So we are limited by the fact that we cannot dig tunnels of thousands of kilometers. I don't know. Of course, if we increase the diameter of the circular collider, we can reach higher energies. But to my point of view, we have reached a limit of for physics collider, particle colliders. So there are two colliders in project, one linear in Japan and one circular with a very high diameter. But there is also a limit, a human limit, because for such huge scale facilities, you need several decades to build them. So if we don't have experimental setups to work on, we will lose manpower because it will not be very interesting for students, and we will also lose knowledge because the next generation that will be able to operate such a facility will never have seen a running collider if it's in 50 years from now.
Good. So I have probably a last question. So it's you mentioned that the new physics will become by considering that you don't have a W or C boson, producing the lepton, the lepton and the neutrino, neutrino lepton.
Yes,
yeah.
yes, yeah.
So it's still this scheme give us a chance to consider or analyze candidates for dark matter or dark matter.
Yes, so you can have virtual intermediate states. So this is due to Heisenberg, these virtual intermediate states of any particles that exist. They will contribute virtually, and in these intermediate states, if there is dark matter, like we have, theorists are very prolificent. I don't know how to say. They produce lots of theories. Each day they have a new theory. Okay, so they propose lots of beyond standard model theory with lots of new ideas like neutralino in supersymmetry. So for instance, in supersymmetry, you have dark matter candidates or postulants. And those can contribute to these virtual intermediate states. Or they can also, when you think you have a neutrino in the final state, since we cannot detect the neutrino, because the probability of a neutrino to interact with matter is so low, we need a huge amount of material to detect them, or in the other hand, we should wait for thousands of years. So we, in particle, in experiments at a collider, the scale of the detector makes that we cannot see the neutrinos. So we cannot be sure that those are really neutrinos. The invisible particles could be dark matter. So we can put constraints on that.
Okay, thank you very much. So I think there's no more questions on YouTube. I don't see also questions here. So I will again thank you very much to Rashi and Professor Isabelle I.Ripp-Baudot. And thank you, Professor Lanson, for being here. Very interesting conversation. And then I would like to give a last short announce. I hope you can see the screen. So this has been the agenda until now. So for next week, you can join us in the talk of one researcher that is located in Paris, Reina Camacho. She will be talking about virtual research and learning in networks like Belle II and Lagrangian physics cases. She's also a particle physics physicist.
We know her, yes.
So yeah, please feel free to join. We will be sharing the Zoom meeting details and the YouTube live stream link. So yeah, thank you very much.